Hey everyone, hope you're doing well. Well, if you've seen earlier videos, you already noticed, but for others, I will give a quick recap of what we're doing. We're building a self-hosted compiler, which is a compiler which is written in the same language it compiles. So we created our own programming language called ELO, and we've built a compiler in Python which we'll use as a bootstrap compiler. And now we're actually building the compiler for ELO in ELO. So how do we do this? Normally, a compiler consists of a Lexer, a parser, and a code generator. So the Lexer takes source code and creates tokens, turns it into tokens. The parser takes these tokens and creates a structure from these tokens. And the structure is taken by the code generator and turned into actual code, in our case, assembly. So that's how we do it. And yesterday we achieved a pretty big milestone because I've written a Lexer in ELO and it's able to tokenize itself. So here's the Lexer, elo.elo. So this takes the argument, which is a file name. It reads the file, so you have source code, and changes the source code into tokens, and then dumps the tokens. So let's see if it works. We can compile elo.elo, the file you just saw, and let's, for example, turn this into tokens. And as you see, this token type, its value, and the line number. So yeah, it works. And then the first time it successfully printed its own tokens. Yeah, that felt awesome because it took me quite some time to debug a couple of memory issues. But the good thing about this is that I was forced to add more tools to the language and to the standard library to help debugging. So what did I add? Well, as I've said earlier, I've added type checking in the Python compiler, the Python implementation of ELO compiler. So if we check this, so the type checker is woven into the parser. So if we look at pushchar like this, we keep track of a stack with types on it, and every time we push something on the stack, we push a type to the type stack. So for example, push char will push the type char to the stack, to the type stack. And for example, when you have plus, you pop from the type stack, you pop those, you check their types, if they're correct, and plus returns a pointer or an integer, depending on the input types. But this is mainly how the type checker works. And so we've added type errors everywhere. So yeah, this is how we catch a lot of bugs. So let's see if we have foo.elo, and we have a main function. We don't care about the input arguments, but we return an int. What if we return a boolean? So it says type error, function main returns incorrect type. So that's the type checker. In addition to that, I've added a debug keyword. So I think I have to update my syntax file. Yeah. So if we have a program, let's say we push a boolean, we push an integer, and we push a string. And we want to know, we want to debug, and we want to know what's on the stack, on the type stack. So this happens during compile time. If we try to compile it, it gives us back the type stack at that moment. So this is very nice to verify if what you're doing is correct. Two major bugs were in the dynamic memory allocation functions in the standard library, which are malloc and free. So we've got a standard library here. We've got a malloc and we've got free functions, just like the C functions, malloc and free. And it was really hard to see what was happening with the memory. So I've created a verify memory function, which is this. And it simply checks all the dynamically allocated memory for invalid metadata. And it has two toggles you can set. Verify memory, if it's set, it like it says, it verifies the memory and the memory metadata. And dump memory also dumps the memory, so it prints the memory to standard out. So let's take the elo.elo file. We set verify memory to true and dump memory to false. So this means every time elo.elo is executed, we verify the memory in runtime. But let's say we also want to dump the memory. Let's build it. Make clean, make elo. And let's say we use that file to tokenize itself. It now dumps the memory throughout the program. So you see a page, you see every block of the page, and if it's free or not, and the addresses and the sizes. So this helped me to catch all the bugs, to debug all the bugs. That's how I got it working. How does the Lexer work? So the Lexer is in a separate library, and it has some, it has a tokenize method. And to turn source code into a list of tokens, we first need to have some sort of dynamic list. So we created one in the standard library. This is this dynamic list, tokens, but the actual implementation of the list is in the standard library. So here it is. I made it so that it could contain integers, but it could also contain like structs, because a token is more than just an integer. So we want it to be able to handle bigger items. But the important thing is that it has a big O of n time complexity, appending to the list if it's O of n, which is great. And looking up an item in the list takes O of 1 time. So that's even better. It's better than, let's say, a linked list, for example. So it's based on an algorithm I got from this video, which is a very interesting video. The channel itself is also very cool. Let's just show it. I'll put a link in the description. Reducible. I hope I pronounce it right. But this channel has a lot of great explanations about algorithms and stuff like that. So this is where I got the idea for the linked list. For the list, it's not a linked list. So I highly recommend watching this video because, well, if you don't want any spoilers on how it works, because how it works is actually very simple. The list is an array of bytes, and all the items are simply next to each other in the memory. And it has a capacity for 2 to the n items. In this case, we start at 1, but it could be, you could start at any point. But the important thing that if an item needs to be appended and the list is full, its capacity is doubled. And this is important. The video explains why that's important. So we created some methods to create a list and to fetch items and pop and append and stuff like that. I built the list to have items of any size, so it works with both integers, and these are integer specific, and structs, which handle pointers. One kind of struct that's important now is the token. These are the offsets. So we've got token type, value, and line, which in total is 24 bytes. And the Lexer, let's see, the Lexer contains this list of tokens. And yeah, the code is actually really similar to the Python implementation. It just checks the first character or the first couple of characters, and when it's a match, it creates a token. So it's really simple. That's the way it works. I think that's about it. Yeah, I want to show that we're actually able to tokenize the tokenizer. So next up is the parser, and in our case, the parser takes tokens and turns them into opcodes, a list of opcodes. So if we've got a parser, like the code generator will be fairly easy. So hopefully the parser won't take too much to implement. So yeah, hopefully we'll soon have a new video with the parser. As always, thanks for watching, and I hope you found it interesting. Please let me know if there are any questions, and I'll see you next time. Okay, bye bye.